So what's that say? Two to the x plus 4. Oh shit. Okay. So there was a section a while back that I forget to weed out problems in the future. All right. Very quickly, this is kind of good. This came up. What are sine and cosine based on? What are all the trig stuff fundamentally based on? Okay, I like it. Ratios of sides of triangles. What other fundamental thing are they based on? Which leads to the most fundamental identities. Where do all the trig values live? Certain geometrical shape. Unicircle, the x. You guys with me? In fact, there's some cool animations where you can have this thing, as it goes around the circle, it can trace out the sine and the cosine. So as you go around the circle, it traces out the sine and the cosine. You with me? So here, cosine be big, and then sine grows and cosine shrinks, and blah, blah, blah. Okay. This is like a typo, or you're wondering if it's related to the h from the limit definition of derivative somehow, right, or something. Yes? This is the hyperbolic sine. This would be the function if we did all the trig stuff, but instead of basing it on a unit circle, we based it on the unit hyperbola. That's trippy as hell. So here is, let's see if Jeff can show off his bad memory. I believe hyperbolic sine, don't hold me to this. I should look it up. I think it's e to the x. I always forget this. Minus e to the negative x over, I gotta look it up. They're based off of exponential functions. So if you see this crop up, you can just pass that problem by. That's fine. It's section 311, by the way, in case you're at all curious. Hyperbolic. So 311 is a section that we skipped. And that's the section about hyperbolic trig functions. And I forgot to try to weed out the future references to those. Is that cool? So which problem was that again? 25? So 25, you could either look up what that is and do it, or not. The great thing about hyperbolic sine is its derivative is hyperbolic cosine. The tricky thing is the derivative of hyperbolic cosine is hyperbolic sine, not negative hyperbolic sine. And you're all like, fantastic. Okay. You guys doing alright? I'm sorry. You guys okay? You're all bummed because the long weekend's over? I like you're all just keep talking about it. Okay. Anything else from homework stuff? No. Okay. I do want to say, let me see if I can bum you out further. Why not? Let's just lean into this bumming out. First, I want to say to all the people who are putting in all the effort in the world, I love it, I appreciate it, right? Just get that right out there. There's a lot of you guys working hard, you're doing honest work, you know where this is going. Some of you guys, it's really obvious you're getting answers from somewhere. Someone, something else. It makes no sense. So if you're getting lower grades than you want to be, and you're not the one doing the homework, well, there you go. That's the easy problem. There's your problem. So I don't want to speak, because most of you guys are not doing that. Most of you guys are doing honest stuff like that. That's fantastic. So okay, so it's not my. If you want that to be your experience, that's on you. You can do that. You can get like if you got it past me, you get a great homework grade, and you can just die on the test, and then you'll fail the class. I mean, it doesn't make any sense to me. I used to do this thing. Does anyone play guitar? Does anyone play a musical instrument? Anybody? What do you play? Violin. Do you have a favorite violinist? No? You're like, they don't know what they're doing. Just wait till I'm out there. So you don't have any. All right. Who else plays that? What do you play? Guitar? Do you have a favorite guitarist? All right, this is so funny. I'm sorry. This is a lot of people say Anders with damn good reason. Yes. Let's say that Jimi Hendrix came back from he said to you, hey, if you send me a video of you playing guitar, I can give you some pointers. I'm kind of busy, but if you send me the video, I can watch it, right? Because he's the guy came back from the dead. He's got a lot of stuff in it, right? You with me so far? And let's say you're embarrassed about how you play guitar, potentially, or you're like, man, I wish I played better. This is Jimmy. So you videotape somebody else playing guitar that plays better, and you send it to Jimmy, and Jimmy's like, hey, you're doing really good. I got no notes for you. Did you get everything you could out of this Jimi Hendrix, not zombie, but back from the dead experience? No, you didn't. Okay, I'm sorry. I am not saying I'm the Jimi Hendrix of math, but I know math. If you don't give me your work, I cannot help you. Most of you guys are. I appreciate that. A decent number of you aren't. It makes no sense. None. Yes? Okay, I'm sorry. Just want to get that. So, yes. Please try this stuff. That's the whole point. The whole point of it. I really love those of you that put little notes in your paper. I used to have people do it all the time. Man, this sucks. Man, this is rough. And I'm like, yeah, yep. Sure enough, that's how it is. If you feel like I am not open enough or like accessible enough, let me know. If you've had enough of me, you've got all kinds of other people to go see. Yes, in the Math Science Center. If they all suck, you got people on the YouTubes. If they all suck, you've looked at them all, which is impossible. Let's say you say that. Then I don't know. Feel it. Okay. I'm sorry. I'll stop. It's just when I'm grading homework, I just don't want to grade ChatGPT, or I don't want to grade a solutions manual. That's not what I'm here for. Okay. All right. But most of you guys are doing good, so I'm going to shut up. Anything else from homework stuff after all that big tirade? Anything left from questions about homework? So homework is going great. Okay. Hopefully over the weekend, after whatever you imbibed or watched or whatever, you do a little homework. We haven't gotten to chapter 5 yet. We did optimization, we did anti-derivatives. Yes? And what's the big thing with anti-derivatives that students always forget and that you're not going to? Plus. So, today we're going to get into chapter 5. And it's going to feel like it's not related to what we just did, because it isn't at first. So I think I laid this out in very vague terms. We're about to do something that's interesting in its own right. And so we'll do that. It somehow leads to a connection with anti-derivatives. And it's not obvious at all. But the connection is so freaking cool. So it's going to mimic a limit definition of derivative for a hot minute. And then we're going to connect it, and then there's going to be shortcuts. Are you guys all with me? Just keep that in mind when we're in the middle of all this craziness. That's like limit definition is only going to be there for a moment. You're going to have to do it, but not forever. Okay. So what the hell are we getting into? I don't know. Oh yeah. The main thing we're going to get into right now, which seems totally disconnected to everything we've done, is areas under curves. Or more appropriately, this is how it's normally worded, but what I really should say is area between a curve and the x-axis. We think of the x-axis as the ground. Okay. Remind me, how many of you guys are going to, that right now your plan is to take Calc 3 someday? Anybody? All right, so what I'm about to talk about is going to come back in Calc 3, but in Calc 3, you're going to be living in 3 dimensions. But it's going to be a beautiful analogy with what I'm about to say. Maybe I'll even talk a little bit about Calc 3. Why not? Sure. You're all like, yeah, you get this Calc 1 stuff, talk Calc 3 now. So if I draw a picture that I remember my teacher drawing the same damn picture every day, and you've seen this from me before. Why? All right. So I have this function from A to B. It's got an f of A. It's got an f of B. And what I'm curious about, for some frickin' reason, is what is the area that makes between it and the x-axis. Okay. And let's talk about why that would be something useful. Let's say this is speed and this is time. Isn't that area going to somehow be a speed times a time? If this was a perfect rectangle, wouldn't it just be this side, which is speed, times this time, which is time? This side, this time. Are you guys with me at all? You guys with me? And I don't care that it is not a rectangle. I can make little rectangles and then add them up. And they would all be a little piece of velocity times a little piece of time. What is velocity times time? What is your speed times how long you're going that speed? It's how far you went, correct? There's that one video of the girl that's, if you're going 80 miles an hour and you go for an hour, she didn't believe you would go 80 miles. So, I don't know if anybody knows what I'm talking about. It makes math teachers really so happy. Okay. So if I found the area under that curve, I would find the distance that this thing traveled. This is its velocity. So it's speeding up, and then it's slowing down, then it's going constant speed, and then it's speeding up. Are you guys kind of with me? That is not an easy calculation to determine how far it actually went. If the damn thing was going at a constant velocity, easy. I would just multiply its velocity times the time. Wouldn't that be the area? So real quick, if I had something going 80 miles an hour, and it went from 1 p.m. to 4 p.m., how far did it go? Yes, it went for 3 hours at 80 miles an hour. That's 240 miles. You with me? What's the area of that rectangle I just drew? So the area is equal to the accumulated whatever the shit. Yes? If this axis is a rate of change of something, and this axis is time, the area is the total amount of that. Words per minute, number of minutes, area would be the total number of words you wrote. Okay, maybe? Do you see how that's generally useful for science? Period. Science, capital S. Okay. All right, look. I do. All right. The teacher's dilemma always is students often need some immediate physical reality for what we're doing to connect to. Well, this one has an obvious connection. Sometimes it's just math, and you don't know. Who knows? All right. This actually has a tie to reality, which is always nice. So, do we have a geometric formula for this? Yes, because you used it. Length times width. Do we have a geometric formula for this? We don't have a geometric formula for freaking microwaved lid. You put something in the microwave, leave the lid on, and you come out and the lid's all like bleh. So we don't, as far as I know, you guys didn't learn that in between trapezoid and circle. The microwaved lid area formula. You didn't learn it. So everybody kind of with me. I don't have a geometric way to get that area. Because I don't have a formula for it. It's a constantly changing height throughout. You with me? We don't have a formula for that. Okay. So, how do we do this shit? So, let me ask you this. How would you calculate the area of this? The little house here. So this is 8, this is 7. And this is 5. How would you calculate the total area of that shape?
Calculate the area of the triangle.
Yes, you would cut it up into parts that you know the formula of the area, correct? You guys kind of with me? So we're with me. I love you guys. So what we do, this is really, really nifty. And in fact, I don't know if you guys remember, I showed you this here, right? This is such a, yeah, we did this, yes? Remember when I cut this up? We did this, yes? And I showed you where pi r squared comes from? Didn't we take a shape we didn't know and we cut it into parts that we do know? We actually repositioned them and shoved them together, but we essentially cut it up into a form that I do have a formula for, correct? Okay. So what we do in this guy's case, this is such a cool thing. You're like, yeah. What we do is we cut this up into triangles. No, let's try it again, Jeff. We cut it up into rectangles. And let me see if you guys kind of get this idea. So if I cut this up into rectangles, can you guys see there's a choice that I have to make in terms of how tall the rectangles are? This might be too detailed of a question to come at you out of nowhere. Can you see what choice I've made in terms of how to tell how tall each rectangle is? How tall is that first rectangle? It goes up as high as what?
Left point.
F of A. Yes, it goes up as high as the left side of its output does. In fact, every one of these goes up as high as its left, well, I tried to. Endpoint does. Okay. I could have done it instead as far as the right endpoint. I could have done it as far as the midpoint. I could have done it as far as any freaking point in there goes. Each of those rectangles, would it be difficult to get their area? So if I told you that the width of each one, well, let's just go full bore. Here we go. If I tell you the width of each one is delta x, why does that make sense? Yes, because if I start here and I go there, x is changed by a certain amount, yes? And I'm going to keep the width of each one the same. Do you all agree that if we get the area of all the rectangles and add them up, it would be a decent approximation to the actual area under that curve? Do you all see that? Does everybody understand what I just said? The physical interpretation of what I just said. If I add up all the areas of the rectangles, which is easy to do, it would be close to the actual area under that curved function. 11. How tall is that first rectangle? So the area of the first rectangle would be f of a times delta x. Yes? We'll say that's a1. Area of the second rectangle, let's see if you guys are cool with this. Area of the second rectangle would be f of a plus delta x times delta x. Does everybody see that? If this is a and this is delta x, what's that? What's this value right there? That's a. This is delta x. What's the value right there? A plus delta x, correct? And that would determine the height of the next rectangle, correct? Do you all agree that if I took the areas of the rectangles, it would not exactly equal the area that I want? It looks like it would probably be a decent approximation, but would it equal it? No. How would I make my approximation better? What could I do? Oh, I like it. Okay. This is beautiful. I wouldn't even think we could go that direction. That's perfect. What are you saying again? Say it again. Oh, yeah. I could kind of, but do you see how I'm over a bit too? So I'm under and I'm over. It looks like I'm more under than over, correct? So I could tell that my answer is probably an underestimate. Okay, so, is everybody really with me now? Now, let go of, holy shit, what's my work gonna look like? Don't worry about that yet. We're gonna make it very, very recipe-ish. Just live with the idea. Does everybody see that? That this is under what it should be. Okay. It would be really difficult for a very complicated function to go back in and try to add in adjustments. I want to make this something I can do quickly. Does anyone else have any idea? How many rectangles did I use? 6. So how can I increase how confident I am in the approximation I get? Yeah, amp up the resolution, yes? How can I be exactly right? What would it take for me to have my answer be exactly right? infinite rectangles, which is not a condition that we're not used to because we've gone to infinity, haven't we, as good as we can. What have we done? We've taken limits. Okay, let me stop for a minute. So everybody get the basic idea. It's sort of like, has anyone ever played any old Atari games from the before times? Has anyone ever seen it? Have you seen Mario, old Mario? Yes, you have. All right, so I'm talking about pixels, yes, 8 bits. And it's amazing how much shit they did with those. In fact, I think there's some new games based on that too, because the look of it's kind of cool. If I crank the resolution up, then it's going to look even better. Yes? So this is kind of like Mario first game. First Mario game. And if I let it go to infinity, that's like what games are trying to be nowadays. Where everybody complains because the ripples in the water don't look right. And I'm like, I play Pong. Okay. All right. So let me do this. This is where we're headed to. We're going to be using expressions that involve these. And real quick, remind me, this, what was this again? What was that for the rectangles? Well, we'll say that's the width here, we'll say, right? And what was this? We say the length or the height, yeah. So in each case, I took the height times the width to get the area of the rectangle. Okay. So let me do this. Let me see if this ties in decently well to this. It sort of does. Yeah, let me introduce this idea. One idea we're going to use in doing this. One symbol we're going to use. Has anybody ever seen, have we talked about that symbol before? Has anyone ever seen that symbol before? Yes, I heard somebody say sigma. So this is the Greek letter S. Math people, we were like, Greek looks kind of like it means business. So let's use Greek symbols to make it look more ooh. And we're like, oh, a sum. Greek letter S. So we use this for summing stuff up. So for example, if I wrote this, okay, if I just wrote that, let me see if you guys can interpret what this means. What value, what's the variable in this situation? Probably the only letter up there is great, besides the Greek letter S. What are the values the variable takes on? 1, 2, 3, kick ass. So inherent in this is it doesn't take on every value 2, 1, and 3, just the natural numbers. So normally these are going to be natural numbers. They could be integers, but are you guys all with me? So the step is by 1. So how would I determine this? What is this asking me to do? It's asking me to sum up the first 3 squares. Yes? So I is 1, what's I squared? If I is 1, what's I squared? So when I is 1, our output is 1. Plus, because this means sum. When I is 2, what's I squared? 4. Plus, when I is 3, what's I squared? 9. So this symbol says, add up the squares of the 1, 2, 3, add up the squares of 1, 2, and 3. There we go. So what do we get? 14. Holy shit. Okay, so that symbol leads to 14. So you can kind of see where this is going. In that last example, we have 6 triangles. They're all going to have very similar looking expressions. I can make it to sum up from I equals 1 to 6 the areas of the triangles, rectangles. Okay, so let me give you this. I want to focus on getting used to this symbol by itself. So there's a side here that says prep for finding areas. The one that's got a bunch of summation symbols. Don't do the side with the upside down parabolas. Hold that for later. right, guys, go ahead and try the first few of these. Obviously, there's a thing to realize about number 3. I don't want you to sit there and go 1 to 38 and go slowly insane. I want you to go quickly insane. If you want to compare notes with other people, that's not a quiz for you, so feel free to work with people near you. So you can see there's 2 levels to these, and you can do each level independently. One is just plugging numbers in, and the other one is adding up the numbers. Kind of shows you a nice way to do the I equals 1, I equals 2, whatever. It's not too weird. Here, while you guys are doing that, anybody not get their stuff back from me? Did I give you your stuff? Yeah, I think so. Oh. Yes. Oh. All right, I'm gonna slowly catch up to you guys here. So if I is 1, I get 2. If I is 2, I get 4. If I is 3, I get 6. So I get 12 at the end. I equals 2, 3, 4. If I is 2, this is 10 minus 4 is 6. If I is 3, this is 15 minus 8 is 7. And if I is 4, this is 20 minus 16 is 4. So then I get 17? Yes. Is everybody good so far? Okay, so this isn't too crazy. If have any of you guys ever taken statistics before, out of curiosity? Yes, so you know this symbol. If you've taken stats, you should have used the shit out of the symbol. So like, oh yeah, this guy, we know. Who got number 3? Who figured out a nice, quick way to do number 3? Yes?
76.
How'd you get it? How do you mean put it in the calculator? You figure out how to do summation in your calculator? Oh, come on. All right, who else figured out how to do it as a human? Yes, human. Oh, it's you in the middle, sure.
Yeah.
Why did you do 2 times 38? Why does that work?
There's no like I after it, so it's always going to be 2.
So it's 2 plus 2 plus 2. And of course, what's the definition of multiplication? I got 38 2. That's the definition of multiplication. Repeated addition, take abs. So the sum of a constant is just that constant times how many of them there are. Okay, I like it. So this would just be 2 times 38, 76. Become a times, okay. So we could make this into, let's see if you guys are cool with this. What is I equals 1 to n of c? Huh? C times n. Kick ass. Okay, I like it. Oh yeah. Sorry. Multiple classes. It's a little better. Okay, sorry. So then I give you this guy. I'm not sure if you guys have looked at this guy yet. This one's got a few things going on. So the way I've given it to you, if you wanted to, you could figure out what f is at the 3 values you need to use, yes? Because this is f of I, yes? Is that cool? So I'm just giving it to you in a slightly different format. I could have made number 1 and 2 in this format. I just didn't. What's the slightly trippy thing about this one? What else is in there? N. What happens to it? Not a Dan, it just comes for the ride, right? Now, if I wanted to, let's see. I'm going to do this in a very silly way and see if you guys, maybe you did it the same way. 1 minus 3 is negative 2. 4 minus 6 is negative 2. Is that right? Yeah, that's a problem, Jeff. 9 minus 9 is 0. I think that's right. Yeah, that's right, Jeff. Maybe. Okay. So then, if I do this, this would be n times negative 2 plus n times negative 2 plus n times 0, which is negative 4n. How we all doing? Is that okay? You guys see that? What I could have done, because we have to remember this is just n times f1 plus n times f2 plus n times. So any summation that has a constant multiplier, what could I do with that constant multiplier? Well, if I'm adding a bunch of stuff up and they all have the exact same thing in them, I could just take it out. I could just factor it out, right? So I could have rewritten this. I could have rewritten this as this. I could have factored the n out from the beginning, because that's just taking out the greatest common factor. Every single freaking term is going to have an n in it, and we just factor the damn thing out. That's a good thing to know. If it's not dependent on I, and it's in every term, I can factor it out. The hardest problem on here is number 5, unless you know the trick. And then it's easy as shit, but I don't know if anybody knows the trick. What would you have to do number 5 directly? 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 5 plus 6. Oh God. Yes? So There is. And here, there's an urban legend behind this. And do it again.
His name was like Gauss or something or something.
Ooh, do it again.
It's something.
I'm
Was
with
it
you.
Gauss?
Gauss.
But it was like something about he was like in kindergarten and his teacher writes this on the board and it was like you won't like add this up and then he just did it in his head. It was like wow.
Where'd you hear that from?
From Professor Greenneck.
Oh, Dan. Okay, Dan. Dan's awesome. I think I told Dan about that. So, the story goes that young Gauss. By the way, you guys remember? Have you guys seen historical records of the way TVs were way back in the day? They had a lot of. I don't want to say it. They had a big back end. They had cathode ray tubes, and if you put a magnet next to one of them, the picture would distort. And if you did it enough, like young Jeff did, it would permanently distort. And then your mom might say, "Who did this shit?" There's a thing you can get, or there used to be, called a degausser. And then it became a button you could push on the TV. It would degauss it. And then they were like, "Why do we have TVs like this? Just let's make them this way." So what are you kind of with me? So Gauss, he did so much shit. He left nothing. In fact, those of you who took statistics, the normal distribution, remember my paranormal shirt that I got? That's a Gaussian distribution because he's the one that came up with the formula behind it. It's like, Gauss, hey, leave some shit for other people. He's got a unit of measurement named after him. He's got the unit of measurement for the strength of a magnetic field. It's named after him. How do you know you've made it in any science? You have a freaking unit of measurement named after you. You have made it. You can now die. You can be fine. You guys got it? Gauss is kind of a big. So supposedly, it was like grade school. Class is going crazy. Teacher says, "All right, I want you to sit down, add up the numbers 1 through 100. You're not allowed to speak until you're done." Right? So he sits down with his papers. Maybe some rest and relaxation. 5 seconds later, roughly, 10 seconds later, Gauss is like, "Yeah, so the other, what are you doing?" You got the answer. It's like, "I got the answer, man. What do you want from me?" So the teacher said, "Shit, 1 plus 2 is 3 plus 3 is..." And it took him, a good few minutes to get the answer. And sure enough, Gauss was right. So here's what Gauss did. Do you all agree that I always forget where to put stuff? Yes. Do you all agree that this problem translates into what we said earlier? 1 plus 2 plus 3 plus blah, 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 blah. 97 plus 98 plus 99 plus 100. Yes? Somebody with me? You're like, "Yeah, dude, that's what it is." So keep going. Okay. So what Gauss realized is, what do you get when you add the first number and the last number? 101. What do you get when you add the second number and the second to last number? 101. So he realized, he went, "Holy shit." He sat there, a little kid, about 6. He went, "Holy shit. I'm just going to get 101s forever." In fact, not forever, but how many pairs of things to add to 101 will you get? 50. You guys kind of. So if n is 100, so we got 100 divided by 2 tells me how many pairs I get, times 1 plus 100 tells me the number they all add up to. Is everybody with me? 1 plus 100, the first and the last, if I add them together, I get the repeated sum. And if I do how many there are divided by 2, I get how many pairs there are, how many 101s there are. Yes? Not only is that a really trippy connection to make, but what's the answer? 50-50. That's weird. Okay, all right. I know I'm a math guy. I know numbers and everything. I know that. But come on, the sum of the first 100 natural numbers is 50-50. Let that be nifty. I love it. This is as much as you get me on. Okay. So in general, what we discussed, is if I want to add up from 1 to n, this would be the how many there are, How many are there then? How many terms would there be in this list? That's insane. Divided by 2, that tells me the pairs that add up to be the same thing. And what do they each one add up to be? The first term plus the last term. So this is for anything. So then if I rewrite this a little bit, I get n times n plus 1 divided by 2. So that is what this sum is. Now this isn't just me riffing on this stuff and telling you stuff you don't need to know. You need to know this. I'm not going to make you memorize that actually, but there will be 2 more things that will become incredibly important, and I think it's 5-2. I think it's 5-2, maybe 5-2. And I will give them to you. In fact, it's on the other side of the paper, I think. Yes? No, it's coming later. I'll give it to you later, sorry. Okay. Don't look at the other side yet. Stop. All right, so that was the answer for this last. What would the answer to this be then? Well, we just did it, Jeff. Oh yeah, that's right. So what if I wanted to do I equals 1 to 1,000? What would that be? Yes, 1,000 divided by, holy shit, times 1 plus 1,000, 1,001 times 500. What's 1,001 times 500? Whole bunch of zeros and stuff. I can't remember. Is it 500, 500? I think so. 500, 500. Okay. Just continuing the. Now it doesn't have to be I could do the sum of I equals 1 to 17. It doesn't have to be a round number or whatever. It's just the formula works as long as it's 1 to something of I. We have a shortcut to get it. You all look appropriately excited about that. This is humans doing shit. Come on, this is neat. All right. So, how does any of this relate to what we were doing a minute ago? So here's how this works. Let me lay down some ground rules. So, let me redraw this little picture. I'm not sure if it looks the same, probably doesn't. Okay. So let me ask you guys, coming back to what we were doing earlier, let's say I use n rectangles. Could you guys figure out how wide each rectangle would have to be to cover that region with rectangles? So real quick, let's do a physical interpretation. You guys all see this wall over here, yes? You're all like, I never noticed there's a wall. Okay, so there's a wall. Let's say I feel like putting wood panels on that wall. Yes? I'm sure the school will be perfectly fine with me doing that. Just throw out wood panels. And I want them to be the same width. Yes? And I want to use 12 wood panels. And let's say I measure the length of this and I get, I don't even know, 36 feet. Yes? So I've got to go 36 feet and I want to use 12 rectangular wooden slats. Yes? You guys are kind of with me? How wide would each one have to be? So how wide would each one have to be? I've got to go 36 feet, correct? And I want to use 12 rectangular slats. So how wide would each one have to be? You guys good? So I do how far do I have to go divided by how many rectangles I want to use. That's a very physical idea. Yes? So what would the width of the rectangles be in this case? How far do I have to go? How far? If this was 3 and this was 10, how far would I have to go? 7. So this is A, this is B. How far do I have to go? B minus A. So the width would be how far I've got to go divided by how many rectangles I want to use. Completely physical idea. Yes? In fact, again, if you took stats, you actually did something like that when you did class width for histograms. You know, like, I don't know, you remember that was early in the semester, Jeff, many times. I'm sure. Okay. Then, if, for example, I'm using left endpoints, and let me define this. This would be x0. This would be x1, Jeff. And then somewhere in here there's an xi. Just a general xi in there. Okay. Are you guys kind of semi with me? So like the first rectangle would start at xo and end at x1. The second would start at x1 and end at x2, so forth. Yes? Just like we did earlier. Okay. So then my heights for each rectangle would be f of a. What's the height of the second rectangle? What's this guy's height? Yeah, f of a plus delta x. Yes? So what's the height of the third rectangle? First, second, third. F of a plus 2 delta x. Yes, okay. So then, this would be x0, this would be x1, this would be x2. I'm sorry, f of x0, f of x1, f of x2. Okay. So if I want to write this in summation notation, this would look like, I'm using n rectangles, so I'll go from the first to the nth rectangle. F of xi times delta x. This approximates the area. And do you even know where we're going to go in the next section? Because how do I crank this up and get a perfect answer? Take the limit as n goes to infinity. Now, if I try to cram an infinite number of wood slats, how wide can each one be? Infinitely thin. So the delta x would become dx. Not 0. Can't become 0 or else I never get away from the one side. 0, 0, 0, 0. I'm not going anywhere. dx, dx, dx. Now I'm starting to move. If I put enough of those together, I start to move because dx is not 0. Are you guys with me? This is a big part of our earlier discussion about infinitesimals. dx is not 0. It's as close as you can get to 0 without being 0. Which makes exactly as much sense as infinity. They're just the same idea in opposite directions. Okay, maybe. Love the answer. You're not letting it out at this point. Yes, sir. Now, in practice, in section 5.1, this is going to be much easier than it might look. This looks very abstract, and I don't blame you, but it leads to a very concrete methodology. In 5.2, if my memory serves, that's where things get a little more abstract. That's where we have to start using stuff like the Gaussian shortcut. But that's going to be like our limit definition is only going to be that for just a moment. And then we're going to develop shortcuts. Okay. I'm just trying to give you a way to power through, because 5.2 can kind of make a student feel buried under a lot of stuff, but I didn't give you a ton of work, and it's only going to be for a little bit. Okay. So let's do this. Do I want to? Yeah, everybody flip your paper over. Let's take a look here. Okay, so how many rectangles do I want to use? So I've got the function. I've given us a picture of it. How many rectangles do I want to use? 6. And I'm going from where to where. Be really careful. I give you the whole kind of like a bigger picture than you need. I only want to go from what to what? 1 to 4. So first thing I want you to calculate is the width of each rectangle. Don't say it. Just calculate it. So in your picture, you can even tell yourself what the hell's going on. 1 to 4. It's not going to be the height of the rectangle, but Jeff, you put a thing on 5. You need your glasses. Oh no. Here, let's try this again. 1 to 4. There we go. I just put that there. So what's my width going to be? 4 minus 1 divided by 6. Be really careful. It's how far I've got to go divided by the number of rectangles. So what is it going to be? 1/2. Cool. So normally on a quiz or a test, I'll do exactly this. I'll give you the picture of the function so you can just work right on top of it. In the homework, you're going to want to do your own rough sketch so you can put your little rectangles inside of it. People that don't trust me that you need a visual anchor are the ones that are going to make silly mistakes. A visual anchor is good. So let's try to draw in. So I want to use left endpoints. So how tall is my first rectangle going to be? One way to answer that is, you already drew it in, Jeff. Isn't my first rectangle going to be as tall as the first input is? And I think, yeah, 1 goes to 1, yes? -1, yes. So it's exactly 1 tall. Where am I going to draw it to? Where am I going to stop and go down? Where am I going to go down? Say again? Not 1/2. 1 and 1/2. Good. So let's see that. 1, 2, 3, 4, 5. Okay. So it's right here, I think. Yes. So I'm going to go like that. Boop. There's my first little ring. Look at him. Look at him. So you might be able to tell already. This is going to end up being. Do you think it's going to end up being an under or over estimate? Because I'm going to be on that side of the hump more. Yes. You guys kind of see what I'm saying? We'll see when we finish drawing this in. And then my next rectangle is going to stop. It's going to be as tall as this side goes to, and then it's going to go over 1/2 and down. So go ahead and finish drawing in the rectangles. Look at my hairy little finger there. Let's see. So then I'm going to draw up, over, and down. It looks skinny. It's too bad. And up, over, down. There we go. Okay. Try to draw in the rest of the rectangles, which I will every now and again call triangles, just because. I'm not good with shapes. All right, so let's see if we have the same picture. What's a really good thing to do to make sure that you've drawn something at least roughly correctly? What can you very quickly do? How many rectangles did I draw? Thank you, guys. So just take a quick second. You know how many rectangles you're supposed to end up with. Sometimes when you start drawing it in, you can kind of go too far and you'll end up more or less. Just do that real quick. Just to make sure it actually matches with what you know is supposed to happen, which is another reason why a visual anchor is good. Now, can you guys now listen, you got your calculators, yes? You need to borrow one, too bad, I forgot to bring them. I can go get them if you want one. Because what do you need a calculator for? How's it going to help you? What's the height at 1.5? Do you want to do that by hand? If you do, tears for you. Special place in your heart. In my heart for you. You guys follow what's happening? Can you guys just take a moment? What's the area of the first rectangle? That's easy, yes. What's the area of the first rectangle? What's the width? Wasn't it 1/2? Yes. And what's the height? So what's the area? 1/2. Okay. Just take a moment and figure out all the areas. So we're going to do this problem not the most efficient way, but I want it to immediately connect with basic geometry. Just find the area of each rectangle. So now you realize you need a calculator to help you figure out the height of each rectangle, yes? What's the width of each rectangle? 1/2. If you know the height, how do you figure out the height of the second triangle? What are you going to plug into your calculator?
1/2 in for x.
No, not 1/2.
1 and
Yes. 1 and 1/2. That tells you the height. Does everybody see that? Why am I using the left side? Because it freaking told me to. The next problem down, you see it says right endpoint. Then I'll use the right endpoint to figure out how tall each one is. So if you plug in your calculator, put a 1 and 1/2 into the function. That's how tall it is. Multiply it by 1/2. That's the area. Do it. I'm even going to show you how to make your calculator give you the exact answer. Does anyone need a calculator? I can go run and get them. You guys good? Okay. Everybody dance now. I'll show you guys a little trick. I think I've shown you this before. If you plug into your calculator the formula into y, like you're gonna graph it, yeah? Okay. I'm gonna go to table set. You don't have to do this if you don't want to, but go to table set. I'm going to start it at 1 because that's where this starts, yes? And I'm going to step by 1/2. I'm going to set this to auto. So now it's going to auto populate a table and it's going to give me, Jeff, not graph, table. It's going to give me all the freaking outputs I want, yes? Very useful. So whatever your width is, you literally just make that delta, this should say delta x, that'd be great, but delta table. Which really doesn't make sense, but it'll be okay. So let me see. So I've got my second triangle, see? My second rectangle is going to be 1/2 times 2.75, then 1/2 times 4. 1/2 times 4.75. 1/2 times 5, and then finally, where'd it go? 1/2 times, what am I looking at? There it is. 4.75. So I get, what is this, 1.375, 2 point something, 2.375, 2.5, and then 2.375. I think that's right. And then just add all those up. Yes? So let's see. 0.5 plus 1.375 plus 2 plus 2.375 plus 2.5 plus 2.375. I get 11.125. Okay. Now, here's a slightly smarter way to do this. I'm multiplying each thing by 1/2. Why don't I just multiply by 1/2 at the end? Right? So one way to kind of make this quicker is to say it's 1/2 times f of whatever plus. So in this case, how am I going to draw in my rectangles? How tall is my first rectangle going to be if I'm using right endpoints? What determines the height of my rectangle for the first rectangle if I'm using right endpoints? Where's the first rectangle going to end? 1.5. So then I'm going to make the height. So all I do is I put my frickin' pen at 1.5 and then I draw up until I hit the damn thing and draw over and down. This is obviously, real quick, do you see how this is definitely an underestimate? Do you see how it went over a little bit but under a lot more? So if I do this one, it's going to be a freaking overestimate. So now I just go over 1/2 up, down, over 1/2 up, down. No. Okay. So now that is an overestimate. So instead of being silly and doing each rectangle and going, oh, that's the area of a rectangle. No, we can take the work and take the 1/2 out. So what's the height of the first rectangle? F of 1.5. And then F of 2, F of 2.5, F of 3, F of 3.5, F of 4. And the great thing about if you have to do left endpoints and then right endpoints is you've already done a lot of the work to get the outputs for a lot of this. Yes, so how did I get the height for the first rectangle in the first problem? How did I know to make it this tall? Okay. This one was using left endpoints. So I know my first rectangle is going to go from here to here. Left endpoint, I go to the left side of it and I draw until I hit the function. So right endpoint, I still know my first rectangle is going to go from 1 to 1.5, but since I'm using right endpoints, I put my pen on the right side of it, go up until I hit the function over. The function output at the point determines how tall the rectangle is. Is that okay? Okay. Yes?
So how would you find the height?
Oh, the same way we just did. How did I find all these heights? I plugged them into the function, yes? So again, the function value at the point determines the height of your rectangle. When I'm doing these problems, the height of the rectangle is equivalent to the output of the function at that point. If I'm using left endpoints, I'm going to plug that point in, and whatever the output is of the function, that's how tall it is. So how tall is my first rectangle? Here, it's the output for 1.5. But don't we know the output for 1.5? Isn't it 275? In fact, I got them all on my calculator, so who cares? So I've got 1/2 times Jeff. 2.75 plus 4 plus 4.75 plus 5 plus 4.75 plus 4. 1, 2, 3, 4, 5, 6. So there's a smart little check is to make sure you have 6 pieces of information worth, because you have 6 rectangles. Some of you guys might realize, now real quick, that's not that hard to put in your calculator, correct? And you're never going to have to do 80 rectangles. That would just be dumb. That would just be busy working. Some of you guys might realize, if you don't realize this, you're fine. If I take the answer I just got and I subtract 1/2 and I add 2, Because what is this guy missing that this guy had? F of 1. What does this guy have that this guy is missing? F of 4. So if I just do that, what did you guys get? Anybody do all this business? What'd you get? If you had, did anybody do all this? Anybody? Anybody? You're all like, we're not going to do what you want us to, Jeff. 12.625. That's what I got by just subtracting and adding bullshit. Yes, okay. So if you, I don't know. This is still a brand new idea to you. But if one is left endpoint and the other is right endpoint, the only difference between the two is to get to the right endpoint, I lose the first point and I put it in the last. That's kind of a quick way to calculate it. If you don't understand what I just said, just do what you did. It's beautiful. So does this match up with what we thought? We thought this was going to be an overestimate. Why does this match up with that idea? Because it's more than this guy. So I kind of give it away down here, don't I? Yes, I do. What I was about to say was, how can I make my estimate even better? Obviously, if I have an underestimate and an overestimate, I can just average the two. So take a moment, if you haven't already, average the two answers we got. I love you guys. Those of you who love the calculator and wanted to do all your work for you, I'm going to show you how to check your work using your calculator. It's going to give us the exact answer. Check your work, not do your work. Yes? True. Of course, people are always like, I showed my work. I told you which buttons I pushed. Let me get there. Blah. What is that? 1.5. So 0.75. So 11.875. Is that right? 11.875. Okay. Now, I'm okay with what we're about to do. It's going to show you a symbol. In fact, it's fine. It's going to show you a symbol that some of you guys know, but I haven't introduced yet. Yes?
Would the average of the sum of the left and right be equivalent to if you had done midpoint?
Not quite.
It's similar.
It's similar. I understand why you may think that, because the midpoint sort of averages as it goes, but it really depends where that falls on the function itself and what the function itself is doing.
In the outside.
Yes, because I mean, if you have a periodic function, then your midpoints or one of the points could end up in every time it's the valley versus the right.
Yeah.
So it depends. Yeah, it depends, but the midpoint will always be between the left and right, which doesn't really say much. So how do I do this in my calculator? Well, if you haven't put the function in your calculator, go ahead and do that. Why is that not changing? Oh shit, what have I done? Oh no, I've destroyed it. Let's see. There we go. There it is. Okay. Now, if I do zoom 6, it'll graph, and it should look roughly like what we got. Yay! Now, here's the really cool thing. I'm okay with this. If you go to second trace to go to calc, we've been in here before. I think we did like the 0. Yeah. You guys see the last two things? Number 6. What's up with number 6? Holy shit! So really quickly, number 6. If I do 6, just go down to it, or just hit the number 6. Pick any point you want to, hit enter, and it tells you the derivative at that point. Yes? Some of you guys are like, man, I didn't know that before. I don't know. You got the calculator. You might as well know how to use it. But okay, I'm not going to tell you that too early, because then people just get it from there. The thing below that, I might as well just tell you the whole idea, because you already know where we're going. We just haven't done the steps yet. Where are we about to go so that by hand we will be able to get the exact answer? We're going to take the number of rectangles to infinity, which sounds like, dear God, I hated 6. 6 sucked. 6 was a lot to write. You want me to do infinity by hand? Yeah, I do. We're going to do infinity by hand. The same way we did before. Limit as n goes to infinity. We're not going to do an infinite number of things. We're going to use freaking knowledge and do less work. if I take, here's what's really, really, really cool. This symbol is very important in calculus, obviously. If I take this summation and I ramp n to infinity, yes? These together mean I have infinite rectangles. So it's an infinite sum. Are you guys at all with me? Do you understand what I'm saying? Okay. We're going to be able to do it by hand because we know how to calculate limits by hand. So it's not going to be that terrible. But these together, they decided to use the letter S. They took the letter S and then they just did this to it. Literally. Well, you know, they didn't have an S and then they went. But this symbol is called the integral. F of xi just becomes f of x. If I make, real quick, did we use every input when we calculated the approximation for the area? Did we use every possible input from 1 to 4? Hell no, we didn't use 1.394. We didn't even use 3.1. You guys with me? I really want you guys with me. So that's why, do you see where it says xi here? So we only use certain inputs to figure out heights because we're approximating. You guys, I need you guys with me. So where the shit did the I go here? Well, do I skip any inputs if I use infinite rectangles? No. Every input gets used. So we're just going to put an x. It's every freaking x. So this becomes infinite sum, which is literally just the letter S elongated. Ooh. This just becomes f of x, and we already know what that becomes. What does delta x become when I make it infinitesimally small? You know this. Dx. So these two things mean the exact same thing. This is the area. How did I get delta x? B minus a. So this is from A to B. This means the infinite sum of the areas from A to B. These two things mean the exact same thing. So if you look in your calculator and you go to second trace to go to calculate, the last one is exactly that, yes? It's going to ask me a lower limit, so 1, and an upper limit, 4. And then it's going to actually visually show you what the hell it's doing. And it gets 12. What was our estimate? No. I think, wasn't the end result 12 something? No, yeah, you're right. 11.875, which was pretty damn close to 12, especially considering this is infinite rectangles, 12, and this is 6, 11.875. Why is that such a good estimate? Because our function is well behaved. What does well behaved mean? It doesn't go insane. Yes? It doesn't have quick changes in direction and all that. How you guys feel? Yeah, how you guys feel? That is literally section 5.1. It's going to want you to give you some little rough sketch, put the rectangles in, figure out the areas, add them up, yes? And then you can check your answer using this set of buttons in your calculator. So here we found 12. Okay. Now, just a quick, I never really talk much about this, and then it's in the homework. Can you guys tell me if I wanted to use the midpoints to figure out how tall the rectangles were? Right? If I want to use the midpoints, I wouldn't put one. What's the midpoint? What's this? The midpoint is just the middle of the rectangles. So the first rectangle goes from what to what? 1 to 1.5. What's the middle of that? 1.25. So I would have put a 1.25 here. And the beautiful thing is, how wide is each rectangle in this problem again? 1/2. So that's 1.25. Plus 0.5 is 1.75. Plus 0.5 is 2.25. I don't know if you guys see what I'm saying. It just shifts the inputs over a little bit. Left endpoint, right endpoint, midpoint. So they want you to do a midpoint. Just figure out where the rectangle goes, get the middle, and then you just add the width. How far away is the next midpoint? The width away. Okay. the way. Okay. That feels like, yeah, this is perfect. It feels like the perfect place for a break. Everybody go decompress for a little bit. Come back 5, 10, 15, 20, quarter to. Let me know if you have anything on your grade sheet wrong or something. Yes? Oh, what's up? Sorry. Yeah, I remember, okay. Remember there's a long blank line. I'll have to look through, let me make this open up. It's possible you left your name off? Maybe?
I don't think so.
Okay.
I mean, it's possible.
So this is my notes page. So Sam.
I know I turned in like 8 seconds before the first test that I took on my video.
Okay. Oh, that's right.
I don't know if maybe there's...
It might be in my office. Okay, okay. I'll find it.
Okay, thank you.
Thank you.
Work is after the break.
Oh, yes. Oh, it's in my office. Let me go grab it. It's finishing printing. Might as well. Look at this problem. So, can you draw the graph? Can you draw what that's asking us to find? And by the way, if you've taken any calculus before, you feel like you've taken it or something, if we have not learned it yet in this class, you cannot do it yet. So if I see anybody doing that, the way we're gonna learn how to do it, that ain't gonna fly for the early parts of chapter 5. Okay. Some of you guys are like, I never took this shit before. Beautiful. Do only what we talked about. That really sucks for you. Some of you guys who are behind on homework, you go back and you do homework and you use things that we didn't know at the time. No. You gotta live within the chapter you're in, whatever homework you're trying to do. So, can somebody tell me, what are you guys trying to do? I want the graph of this. So, what's a very obvious thing? I mean, what's the first input that this region wants? And what's the output for an input of 1? 0. Okay, so at 1, it's at 0. And I want to go up to 4. So, what is the curve that I'm living under?
Straight line.
2x minus 2. Yeah, so it's what a mathematician would call a straight curve. So all I'm going to do now is just, at 4, what's the output at 4? 6. Let's see. 2, 4, 6. So what shape have I just made? Triangle. Do I need calculus to answer that question? This is a very calculus dominant symbol full thing, yes? Okay, pretend like I just said all those words correct. That is very calculus symbol heavy. But to answer the question, if I understand what it's actually asking, find the area under, okay, if you draw, it's a freaking triangle. What's the area? What's the height? 6. What's the width? 4. The base, right? It's 4. So area of the triangle is 1/2 base times height, because it's half of a rectangle, correct? So 1/2, 4 times 6. 12. Yeah. You guys, are you with me? There will be problems exactly like this one in the homework. And they'll say something like use a geometrical interpretation to get the answer. Maybe. So this is a problem where I don't need to use frickin' rectangles because it's already a shape I know. It's only the ones that are curvy that I'm like, oh shit, I don't have a formula for that. Let me up the stakes here. What if I wanted this instead? All right, graph that. Show me, do the region that that's referencing. If you're just coming in, good luck. Try and do. Yes, Jeff? No, I'm just. Hello. 2, 4, 6, 8. So at 1, it's where? Holy shit. And at 4, it's where? 8. What did I really just do? I really just took our triangle and shifted it up. So now you could either look at it as a triangle with a rectangle, or you could look at it as a what? Trapezoid. You can look at it as a trapezoid, yes. Why is that a trapezoid? Good. The bases are parallel to each other and the other sides aren't. So trapezoid is officially a quadrilateral with exactly 2 sides that are parallel. Some people say it's at least, but it's exactly 2 sides, yes.
So basically, you're just plugging in values to get the height.
Do you agree with me that 2x is the function that we're living under? Sort of like that parabola was what we were living under before. And I want 2x to exist from 1 to 4. So I just plugged a 1 in to see where it was and a 4 in to see where it was. This says, what's the area between that and the x-axis? Yes?
What's the point of the dx being?
Oh, so the dx is beautiful. The dx is this, and the function is this. And to get the area of something, I need to multiply this dimension by this dimension. Yes. So agree with me? Sort of. No, it's pretty good. So the dx would be related to the 3. And then this would be related to the heights. Yes? Yes. The area under that line. Or between, even better than, you hear that all the time, but it should be between that line and the x-axis. So again, one way to do it is, do we know the area of this triangle already? Isn't that the same triangle from the first part? Just looked it up. Do we know the area of the triangle already? Sure. What did we get? 12. So this area is 12. What's the area of this rectangle? That's the only part that I don't have yet, right? So how tall is it? What year is it? How tall is it? 2. And how wide is it? How wide is it? No. 3. So what's the area of this rectangle? 6. So then what's the answer to this? 18. Done. Yay. Okay. Is it possible to get negative area from this? Of course. Is it possible to have a shape in real life that has a negative area? No. No. Not as far as we know. We're not talking about some kind of weird black hole kind of like. No. You guys know. So like when students would answer a question about building a shed, they say the length has to be -5 feet. I'm like, what are you making that thing out of? I'm not going to go in your shed. I'm going to go to the Stranger Things thing. I'm going to go to the underside, under whatever the hell. It's been too long. Okay. So for example, if I would have said, okay, let's see if you guys can handle this one more time. Interval 1 to 4 of, you can do it, Jeff. 2x minus 8. That's perfect. Dx. What this would look like now is, see if you guys can handle this. When I plug a 1 in, I get -6, yes? 2, 4. When I plug a 4 in, I get 0, yes? You with me? So then it would be this. It's always the area between the given function and the x-axis. really want you to understand. You will have calculus teachers who will not agree with what I'm about to say. And what I say to them is, you're entitled to be wrong. That is negative area. Why is that okay? It's not a physical thing. If that was the distance from my house and my velocity is negative, that means I'm going back to my house. So what's happening to the distance from my house if I'm going back to my house? It's getting smaller. So I'm losing distance. This would be a loss of stuff. Right? If I get paid so much money, I gain money. Doesn't my employer then lose money because they're giving me money? So there's two sides to everything. If there can be a positive area, meaning I accumulate something, somewhere else they're losing it. So that's what negative area means. I'm not saying you have a physical negative area. I'm saying that if this represents money, this would be a loss of money over time. Yes? Unfortunately, that makes physical sense. Young Jeff in college knew all too well. The bank accounts can be negative. And then they still charge you for that. I'm like, I don't have any money. All right, sorry. I'll be right. I'm still better. So how do you get this answer? Yeah. So what's the width? 3. And what's the height? -6. So what's the area? -18. Do it again. Divided by 2. What do you mean? Oh yeah, half of that. -9. How's that sound? 3 times 6. Did we get the first one right? No, screw it. That's okay. We got the idea. That's all we need. We got the idea. We'll be fine. Okay. You guys kind of with me? So my point with that last problem was the answer to an interval can be negative. I think I've used that word before. This is what we call an interval. So an interval is just a sum of rectangles where we let the number of rectangles go to infinity. So a problem we can't currently do would be this one. This is a very simple problem that we cannot currently get the exact answer for. Because if I graph it, I'm going to get curvy dude, and I don't have curvy dude geometry formulas, right? If you took curvy dude geometry, I want to know. I'm not going to do this. All right, how are we doing? You guys gonna? So don't forget, when you see that S, that symbol, it looks like an elongated S. It literally is that, and it just means sum up an infinite number of rectangles. I like the way it just said, it's just summing up an infinite number of rectangles. Because if I would have told you that outside of the context of this class, you would have looked like I was crazy, right? I don't blame you. Okay. So let's do this. We've got section 5.1 down. Most of the problems are going to be variations on this. There will, of course, be some conceptual problems. So try those out. You've got this little template to go by. Okay. So let's talk about, you're not going to believe this. We're going to talk about section 5.2. 5.2 now says, 5.2 is where we allow the rectangles to go to infinity. This process gets a little crazy. So let's do this. Let's try a simple example. Let me make sure I don't do the example. What was that one? That was just that. Okay, good. Hey, let's do one. Yeah, sure. Okay. Let's do. Should I do that? No, I'm not gonna do that. Let's do this. I want to know the integral from 0 to 3 of x squared. We'll just do this. So we could graph that, we could estimate it using rectangles, but I'm using this symbol, which means I want to know the exact answer, which means I want to ramp up my resolution to infinity. So what that means is, I need to evaluate this. All right, there's a lot of little parts to that. So these two things are fantastic. At the moment, I don't give a shit about them because they don't require any work from me. I need to figure out what that is. I need to figure out what that is. And I need to plug that into F. You guys see what I'm saying? So there are three parts of that require me to figure out what they are so I can shove them in. First thing, let's start with delta x. What is the formula for delta x always? B minus A over M. That cannot change because it's a physical idea. Go this far, use this many steps, this is how big each step has to be. So what are B and A in this problem?
3 is B and 0 is A.
Yeah, 3 minus 0 over n, so we get 3 over n. So what sucks about 5-2 is we're not going to get numbers. We're going to get things dependent on n. We're going to get things dependent on I. Why? Because I'm trying to use an infinite of rectangles. I'm not using 7, I'm using infinite. So I'm using n rectangles, and then I'm letting n go to infinity. And that's what gets students down. Even in calculus, you guys should be so cool with freaking using a bunch of variables. But a lot of times we're not. Okay. So always get delta x figured out. It's the one that controls everything. If I know how far I'm moving, then I know how to figure out what xi is. So if I start at 0, let me think. Okay. In general, xi is going to be, let me see if you guys are cool with this. If I start at A in general, how do I get to the next input? Yes, so it'd be A plus delta x. And then to get to the next one, it'd be A plus 2 delta x. So so if this is the first one, this is the second one, how do I get to the ith one? How many steps do I take to get to the ith? So how many steps does it take to get to x1? x2. So it would be A plus 1 delta x to get here, A plus 2 delta x to get to x2. So how many steps does it take to get to xi? How many steps to get to x3? 3. How many steps to get to x4? How many steps to get to xi? I. All I is they didn't tell me what number it is. If they say x7, I go 7. 11. I. There you go. We're good. Whatever the shit I is, that's how many steps it takes to get to it. Yes? And I keep thinking about the freaking Tootsie Roll Pop. Because I keep saying how many steps it takes. How many looks does it take? Okay. Sorry. So we know what delta x is. So xi in general is A plus I delta x. This many steps. I desperately try, even though I can't write in English, this many. I don't like vowels. Okay, this many steps. I try to get people to understand you can read a lot of mathematics in English. Start at A, go, I steps. That's what that says. That's how I get to the ith rectangle. Okay. Let me stop for that. Now, if you don't understand my attempt at translating this stuff into English, it almost doesn't matter. It would be great, but you just have to do these steps. These are the steps to do. I do have a handout I'm going to give you in a minute, but it's got too much stuff on it. I don't want to. So you'll see all this stuff on it. Very recipe-ish way to do this. Okay. All right. So, what is xi in this case specifically? So in this case, we know delta x is 3 over n. Xi in this case, what's A? 0. Plus I delta x. So xi is 3i over n. Is everybody cool with that? You guys see how I got that? If I integrated from 2 to something, this would have been 2 plus 3i over n. You guys see that? When I use 0, things just simplify a lot better, but that's why I simplify, because it's 0. So I know what delta x is. I know what xi is. Does anyone remember what the next, what does that summation thing need from me? what am I supposed to do with whatever the hell xi is? I'm supposed to plug it in, yes? And what's my f? What's my function? X squared. So f of xi is equal to f of 3i over n because xi is 3i over n. And here's where you guys just gotta, what's my function say to do? Whatever the shit you put into it, you square it, yes? So then I'm gonna square this. So what do I get? Yeah, 9i squared over n squared. All right. So now I've got all the parts that this guy needs from me. And just keep reminding yourself the physical reality behind this. This is a rectangle. Height times width is the area. This says add up all the rectangles. This is the weird part. This is where it says let yourself have an infinite number of rectangles, right? So that's why we do him last. He's the last thing I worry about. So now let's just put all this stuff together. Let's see what this looks like if I put it all together. Ooh, I'm turning the paper this way, so you're like, oh shit. So let me put this down again. Limit n goes to infinity. Sum I equals 1 to n. F of xi is this. And then times delta x. Delta x. What was delta x? This is where it's really easy to make a mistake. What was delta x? Good. I'll get people to put this there. That so sucks. That's xi. Delta x, 3 over n. By the way, when I say people, I mean me. I've done that before. And that's exciting. Okay. So how did I get what I just put? Well, okay. We know this is the idea behind the whole thing. This is how to get the area between the x-axis and the function. Yes? We built this up. So now I'm just, for this situation, let me just calculate each piece it needs. It's 1, 2, and then shove it in there 3. So 1, 2, 3, and then I just got to put stuff in. Now, can somebody simplify that just a little bit?
Be 27i squared over n.
Yeah, it'd be 27i squared over n cubed. Kick ass. Oh, did I forget? Oh, no, I did. Okay, look at me go. So let me ask you a very strange question, potentially. What does the limit see as a variable? N. What does the summation see as a variable? And you see why? Because the summation I is changing and the limit n is changing. You with me? Now everybody, 27 is without a doubt a constant. Couldn't I pull a 27 out? And I really went, this would be 27 times shit plus 27 times other shit times plus 27 times other shit. Couldn't I just factor 27 out? Of course I can. So that's just factoring out a GCF. What else is a constant according to this guy? N cubed. Yeah, n in general. So I can take 27 over n cubed. I can take it out here, but I definitely can't take the over n cubed out here. Wow, just to let you guys know. Okay. What we're doing today is big. What we're doing today is huge. Derivatives, oh, they're cute. Integration is where it is freaking at. If you do any stem after this at all, you're like, how do I do anything without integrals? So this is kind of big. So I feel the pressure on myself, just to let you know. I want you to really get the idea of this, because this is huge. This is the entire rest of the class, and then this is potentially a lot of the rest of your courses, especially if you're taking Calc 2 and Calc 3, obviously. But even if you're taking biology, chemistry, whatever, physics, if you're taking count based, you're going to get a lot of integration. It's everything. Okay. So I could rewrite this as the limit as n goes to infinity, and what I normally do is I just keep these collected here. And what's the only thing left inside of here? I squared. Now, we know what the sum I equals 1 to n of I is. That was good old Gauss did that for us. That was n times n plus 1 divided by 2. Yes.
Could you explain what you just did?
All I did was the 27 came out and the n cubed came out. Just factored them out. Yes? Okay. Maybe it's good for, let me take a quick side note here. Like you teach in the damn class, you can do whatever you want to. That's true. So if I had this here, is there a GCF? What can you take out? You can write 5 over m squared once in front of this sum, yes? So I could take that out of the sum and put it in front of it, correct? Because then I could just distribute it back. So all I'm doing here is every term, the sum, it would be 27 times something divided by n cubed, 27 times something else divided by n cubed, plus 27 times something else divided. So of course I could take a 27 over n cubed out. I'm just factoring it out. Okay.
On the test, can you put a parentheses around the sigma, or would that change it?
Like this?
Yeah.
Totally good. I love it. Nothing wrong with that. Kick in Z acid. Now, it might not surprise you. Let's see. If that square wasn't there, what could I put right there? If that square wasn't on the I just said it a minute ago, what could I replace that sum with? If it was this, what is that? Gauss lives in the urban legend for you. It might not have been true, by the way. It's just a guess we made and based on stories we heard. Who knows? What's this? Yes, I can replace this with n times n plus 1 over 2. Jacob's like, I was going to tell you that. You cut me off. I'm sorry. That's not what I have, is it? Damn it. So, not surprisingly, this also has a shortcut way to rewrite it. It's not nearly as obvious. I cannot easily show you why this is true. And in fact, this is the one I always forget. Oh, yeah. So I really want you guys to understand, if it was this, I would put n times n plus 1 over 2. Why? Because that's what that is. We actually, we didn't really prove it, but we gave enough evidence to seem that it seems like logical. This one I'm just going to give to you. And I just looked at it and I forgot it. But I think it's this. Shit, don't think. N times n plus 1 over 2 n plus 1. Yes, okay, good. N times n plus 1 times 2n plus 1 divided by 6. Let me write that again because I wrote it really tiny. And it's on this handout I'm going to give you anyway. So it's n times n plus 1 times 2n plus 1 divided by 6. Yes?
Is this something we're likely going to need to memorize?
No. I already told you that. I'm going to give you these. In fact, there's a third one. You're not going to believe what it is. I'm going to give you all 3 of those. Yeah. Yes?
Now, because we only have one variable, it's easier to find the limit, right?
Yeah.
We don't have the variable
Yeah.
limit.
We actually did the sum. Now, real quick. Well, let's finish this up, and then I want to come back to make this connection stronger. If I was a better teacher, I would have done that already, but someday. Does everybody understand what Sophia just said? This is now a chapter 2 problem. Yes? Do you guys see that? What's the degree of the top? Should you multiply this out? Dear God, don't. But what's the degree of the top? Third degree, yes. N times n times n is n cubed. And what's the degree of the bottom? Third. So what's this limit going to be? The ratio of the coefficients of the highest degree terms. So on the bottom, it's obviously 6, yes? What is it on the top? 27 times 2. Yes? Do you guys see that? Do you guys see that? Real quick, if you don't quite see it. So this would be, what comes out? So this would be 18 over, is this 9? Wait. 9. No. Yes. Okay. If you don't quite see that, look here. Let me write this by itself over here. If you were to multiply the top out, what's the first term you would get? 27 times n times 2n. Yes? That would be 27 times 2n cubed, yes? So what's the coefficient of n cubed on the bottom? 6. What's the coefficient of n cubed on the top? 27 times 2. How do you see that really quickly? 27 sit right there, and 2 is in front. So it would be the coefficient of the highest degree term. If you multiply it out, no need to multiply the damn thing out. You guys like to multiply your stuff out, and that gets crazy. Almost never do it, yes. I'm going to give you some of my squared, some of my cubed. Some of my cubed is trippy. Not because it's freaky, but because it's simple. Okay. So what did we just figure out? This is my favorite question to ask because everybody's like, I have no idea. We did a bunch of N's and I's. What does 9 mean?
The sum of all of the rectangles and the area.
Yes, that's the area under the parabola from 0 to 3, or the area between the parabola and the x-axis from 0 to 3 is 9. It's a nice number. That's nice. Can you guys, let me see. Let me make a connection for us right now, and then I'll come back and focus on this connection here a little bit. What's the antiderivative of x squared? What power would it be? It would be to the third power, yes? And then I divide by, yes? Plus c. Okay, what is that? What's the value of this at 3? What do I get when I put a 3 in? 3 cubed is 27, divided by 3 is 9 plus c, yes? What's the value of this evaluated at 0? C. What do you get when you subtract these two things? Holy shit! Which is exactly what we just got, yes? Now listen. What I just said, you don't have to know yet. But there is a connection between an antiderivative and the integral. It's not obvious why there should be, not yet. Okay, but there will be. That's going to be the shortcut. We know how to do antiderivatives. Integration, if I wanted to integrate something, I'd have to do all of this. Do you want to have to do all of this forever? Do you remember doing limit definition derivative? Do you understand now my analogy? We had to do limit definition derivative for everything for a while, and then we learned shortcuts. We're going to have to do this for a little bit, and then I'm going to immediately show you the shortcut. Yes? Okay, I like you guys. I love you guys. Okay. Yes, I want to show a connection. So, here, let's do a specific example of what I just did earlier. What was it? Here we go. Yes. A 1 to 4 of I squared. So what is this? This would be 1 plus 4 plus 9 plus 16. Is that cool? Which is what? Yeah, 30. Now, if I use the rule says this is n times n plus 1 times 2n plus 1 divided by 6. What is n in this sum? What's taking the place of n? 4. So n is 4. So 4 times 5, you with me? Times 9 divided by 6. Let's see, that would be 180 divided by 6, which is 30. Same freaking thing. So is that a proof of the n times m of this thing being the same as this thing? Oh, hell no. Does it at least show you there does seem to be a connection between the two? Oh, hell yes. How could you prove that? You would use something that sounds like mathematician became a dentist. It's called math induction, or it sounds like some kind of weird, like an induction oven or something. Or is that convection? Yeah, it sounds weird. Math induction. It's a proof method. Do we have time to do it this summer? No. So you guys are like, thank the gods. There is a way to prove this. But do you understand what I'm trying to do here? We show the actual sum versus the predicted sum. So this, not even just predicted, but this is what the sum will be no matter how high I go. So if I go to 40, do you want to do it this way? I'd much rather just put freaking 40 in here and figure out what the shit it is, yes? If you see the sum of I equals 1 to n, I squared, you could replace it with this. Yes?
Why is it over 6? All the numbers. Why 6?
Oh, I love that question. You don't even know. It's sort of like sitting and watch Doctor Who. And what does everybody say for the first time when they come in the TARDIS? What do they say? Yeah, exactly. Although somebody said it's small on the outside once they throw them off. But I kind of live for that kind of thing. In statistics, I'm sorry, I keep going back to the same person, but yes, I do. There's a formula for the average of a uniform distribution, and it's divided, the standard deviation of it is uniform, and it's divided by 12. And I wait for somebody to go, why is it 12? I'm like, because of calculus. We can't show you, because most of you guys don't know calculus. The over 6 would come out of the proof of this, which at the moment is a little beyond this. Yes. It's just because. So here's the nifty thing. You ready? What do you understand? The sum here. The sum of I is Gauss dude. Yes, that's beautiful, and it makes sense. That's the pairs. This is the repeated sum. Beautiful. The sum of 1 to n of I squared. We all know that should be more difficult. Because now I'm adding the squares of things. Those don't go together. This should be a more disgusting thing. But like Brendan just put out there, why the shit specifically, Jeff, is it 6? And for right now, all I can say is reasons. And then we have this guy. This guy, to me, is the coolest thing. This is so... Now, do you see how much trippier this got? So what is this going to be? Well, actually, I have to turn the paper. No, I don't, because it's just this, which is so beautiful. Does it make sense? No. Why should it be that? There is no reason it should be. It just is. Okay. So if you are interested in the proofs of those, if you remind me, I could even type it up and put it up on Canvas or something, if you want to see it. Okay. If not, great. We're just going to use it. Okay. So let me do this. I'm going to give you this guy. This guy's got an example on the front. It's got the kind of template for how to do these things. You're welcome. This is a beautiful thing to have out next to you as you do this homework. Wow. Uh-oh. So, let's take a look at this together here. Very proud of this little worksheet. It's very nice. It's got color and everything. So here's that little 3 steps, yes? Step 1, I kind of consolidated. Delta x leads right into xi. Whatever xi is, you plug it into the function. and then you put those things into this. Those are and that's setting it up. That's just getting the problem ready. Which is why I didn't give you a ton of these, because they do kind of take a while. Okay. Did I give a more interesting one on the back? A little bit, okay. Yeah, the back is definitely more interesting. We can do that, okay. So here's a worked out problem. Over here, look. This one we saw earlier, remember that? The sum of a constant is just c times n, that's because it's got that many c's. And then here's the three big dudes, yes? Bam, bam, bam. So on a quiz or a test, those will just be sitting there. These three. This one you have to know. I know, I'm evil. If you're not used to that yet, pay more attention. So on the back, this is kind of a general review of stuff. Number one should be quick. Oh wait, did I? Is that the same? That's not the same one, no, right? That's a different one, yes? Yes, it's different. Okay, good. I like upside down parabolas because they just make sense, but don't get too used to them. I can give you whatever the hell I want to, but try to do number one. That'll be a nice review. And then try to set up number two. You can try to do number two, but we can do it together. So do number one, at least set up number two. And then I'll come in and do number two with you. Oh, what'd you figure out the delta is? Oh, you're using 4 rectangles, yes. So your width was, what is it, 3/4. So make your delta table. Yeah, you did. And then you're starting at 0 though, right? So make your table start 0. And then hit now hit table. And so now you have all your alphabets. Yeah. Cool. So one thing you can do for yourself, when you figure out the width, you can immediately just plot your endpoints, your inputs. So you have 0, 0.75, blah, 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 blah. So even if you're gonna do right or left, these same numbers are gonna come up. So I'm doing left endpoints. So that first rectangle goes from 0 to 0.75. How tall will it be? This one you can tell me exactly. The first rectangle, how tall will it be? 4, yeah. Because it's the left endpoint, so it's going to be the left output. Oh shit, Jeff. Got a little excited there. There we go. And then the next one is going to be as tall as whatever the output is for 0.75. The next one's going to be the output for 1.5. And the last one will be the output for 2.25. Can anyone tell me why it doesn't matter on this problem if I use right or left endpoints? No. If I was just doing number 1, that's the only thing I care about. Why does it not matter if you use left or right? What I mean is, why with the left and right endpoint give you the same answer? Ah, there it is. Because it's symmetric. Why am I sitting down? I don't know. Because the area I'm going over is symmetric, right? So right now we're doing left endpoint starting at 0 to go 3. If I do right endpoints, I can think of that as doing endpoints from 3 to 0. It's the exact same rectangles, just shifted. I don't know if you guys are with me. So if the region I'm going over is symmetric throughout, I don't care if I do right or left. They're going to be the same damn answer. So you see how one side underestimates, the other side overestimates. Anybody? Where's the vertex of this thing? I appreciate that answer. That's all. What's the x value of the vertex? Does anyone know what the x value of the vertex is? What's the output at 0? What's the output at 0? 4. What's the output at 3? 4. So the vertex must be right between them because the vertex is where the mirror is. So 1.5. That's where the vertex is. Right? So these guys underestimate, these guys overestimate. If you flipped it, the overestimation would be here and the underestimation would be over there. You get the exact same answer. Do you have to know any of what I just said to actually do number 1? No, but it's generally good to know. So now I've got my width times my function evaluated. What's the first thing I'm going to evaluate the function at? Using left endpoints. So what's the f of? I see somebody mouthing it to me, f of 0. Plus f of, now I just step up 0.75, plus f of 1.5, plus f of 2.25. Do you guys see how somebody could make a mistake and put one too many f's in there? They would say like f of 3. You're just kind of going along, f of 3. How many rectangles are represented at the moment? 4, yes? If I put one more f in, that's 5. And I don't want 5 rectangles. I'm trying to help you with some really common pitfalls. And again, you could do the same thing we did before. You could put in here 4 plus 3x minus x squared. Scheisse, I gotta delete this other shit. There we go. And then if I do table set, I want to start at 0 and I want to step by 0.75 because that's my width. Go to table and now I've got my outputs I need. So I got 0.75 times 4 plus 5.6875 plus 6.25 plus 5.6875. Okay. Oops. I get, what'd you guys get? 25? Oh, did you multiply by 0.75? Plus, you also got 25? What did I do?
My rounded answer was 16.219.
Yeah, 16.219. 21875? Yeah.
Yeah.
I'm not sure, where's people getting 25? What do you, is that, let me see.
Oh, and I've multiplied by 1 instead of added, so it's fine.
Oh, okay. Okay. Did several people do it? Okay. How do you guys feel about this kind of problem just by itself? I tell you, use this many rectangles. I'm not going to do more than like 6 normally, because then it just becomes busy work. You identify your width. That kind of controls everything after that. What I really love about this is physically, can you guys see what I mean by that? The width controls everything after that. It tells you what you're going to input. It tells you what to start doing, blah, blah, blah. When we go to the next level, where we start letting the number of rectangles go to infinity, the width is the first thing I have to calculate, because then everything else flows from that, which kind of reinforces what I just said. So, if I were to do right endpoints, I would have gotten the exact same answer. Oh, here we go. Oh, today doesn't matter, because I can't do anything to the lights anyway. Let me see. So here, what do I start with? What did I just say?
You want to calculate the change in x.
Holy shit, okay. So what would delta x be here? What's my b and my a?
0.
Yeah, so it'll be 3 minus 0 divided by n. So my delta x is 3 over n. Sounds familiar? Why'd I do 0 again? Ah, that's too bad, John. That's okay. What do I go from there?
You want to find the ix.
Yeah, the xi. So that would be a, which is 0, plus yeah, it'll be how many 3 over n's?
Oh,
I of them. Good. So then I get 3i over n. So again, this kind of sucks. Past Jeff wasn't thinking ahead too well. If I started at 1, there would be a 1 here. Everything would be a little worse. Okay. So I figure out what delta x, which helps me figure out what xi is. And then what do I do with xi?
You want to plug it into our function.
Yeah, plug it into your function. So at least this level is worse. So I got to plug in 3i over n. So therefore I would get 4 plus 3 times 3i over n minus 3i over n squared. Is that cool? Just plug a 3i over n, just plug it in. What we just did is we evaluated an infinite number of inputs. Go team. Yes? What'd you do today in class? Evaluated an infinite number of inputs. What'd your lazy ass do today? So that's pretty good. And now we just throw that business in. Yes? So what we really just did, can somebody else tell me a different way to interpret this? What do I get when I plug stuff into my function? What do I get? The what of the rectangle?
The area. Oh,
That's
the
delta
height.
x.
That's the height of the
That's the height. So when I plug it into the function, it tells me how far up I'm going. Yes? So I just figured out all the heights for all the n rectangles. This is the width of every rectangle. And now I just have to multiply them and add them all up. Yes? Yes? So, what part of this am I going to do last? Limit. So, at first, how many rectangles do I have? N. I have n rectangles. Yes, that's why my width was 3 over n. So I'm not doing this because of the infinite part. I would do it no matter what. It's if I let my n go to infinity, I'm going to get a perfect answer, not an approximation. It's going to perfectly match up. I'm not sure if I answered your question. You were asking, did I figure out what f of xi is because of the infinite? No, I did it because this needs it. That by itself is the sum of the areas of n rectangles. Like if I use 6 rectangles, there would be 6, that would be the sum of the 6 rectangle areas. So that it needs it no matter what. And then I am eventually going to let n go to infinity. So just to kind of show you, could I approximate this using one big ass rectangle? So watch. I could do this. Let me approximate this using one big ass rectangle from what was it, 0 to 3. So if I use a left endpoint, here's my approximation from 0 to 3. Whoa! Do you think that's a good approximation? That approximation sucks. Yes? How do I make it better? Well, I use more rectangles. So how do I make it the best? I use all the rectangles. So I use infinite number of rectangles. So the more, if I make the rectangles really tiny, they're going to fit this curve better. So if I make them as tiny as I can, they're going to fit it perfectly. So I need you to understand, this step right here is not generally necessary. It's just me saying, I want to make this better. I don't want it to be some crude thing. I want it to be perfect. I want the resolution to infinity. Not Mario, not even frickin' whatever the shit is people play nowadays. I want it to be like perfect, infinite. Okay. So what does this piece need? It needs delta x, we got it. Right there. It needs xi, we got it. And it needs f of xi. We got it. Now we can plug it in. This goes in here.
Can you lift it up?
Oh yeah, sorry. And then delta x goes at the end. And delta x was 3 over n. So that's just me shoving all those pieces in. Yes? And I'll tell you this, on a test or a quiz, I will give you this, and what I normally do is I like part A is find delta x, part B is find xi, part C is find f of xi, and then I say, now do the thing. I just gotta shove them all in. Yes. So we shoved them all in. What's the first immediate thing I can do to start to simplify this? Good. Distribute the 3 over n. You need more space, Jeff. All right, there you go. All right, so then we get 12 over n plus 27i over n squared, not plus, minus 27i squared over n cubed. Okay. Now really quickly, let me really date myself. I would listen to my 8-track tapes as I balanced my checkbook. No. Not that old. My mom actually had 8-track tapes, but they were pretty old even for her. Back in the day, you had to balance checkbooks. I'm almost certain nobody here does this. Does anybody balance your checkbooks? So, balancing your checkbook would be take all the deposits, all the withdrawals, yes, all the things you have to pay. If I had to add and subtract a bunch of shit, couldn't I add up all the deposits and then add up all the expenditures? And then add those together? You with me? This is really silly what I'm saying, but you're not used to summation notation, most of you guys. I'm not going to distribute the sum symbol. If I have to add up this plus this, couldn't I add these up, and add these up, and then add all those together? Maybe? This is like my deposits, this is money people gave me, and this is my expenditures. instead of doing this for each thing, I could add all these up, add all these up, add all these up, and then add all those together. So what I'm saying is, I'm trying to be very careful. I'm not, okay. How do you say this, by the way? You would say this, the sum of this from 1 to n, not the sum times. This is not multiplying this shit, yes? Just like if I put natural log of, Jeff, natural log of x plus 1, I can't distribute that. That doesn't make any sense for several reasons, yes? But, with all that said, it sure looks like it distributes, because I'm just going to write this. Get out of there. Did I leave? No. Okay. So I just sum these up, sum these up, sum these up, and then sum those up. So do you see how it looks like it was distributed? But we know better. So you guys look confused. So I'm just adding up all the 12 over n's. And to that, I'm going to add the sum of the 27i over n's. And to that, I'm going to subtract the 27i cubed over n squared. Okay. Now, I just want to point this out. Nobody's asking me a question, but several of you look like you're in pain. Is everybody doing okay? It's pretty okay. Real quick, watch. Watch. This is going to be silly, but that's okay. Look. If I had to add these things together, do you see how I could add 4 and 6, 7 and 3, 11 and 9? Don't they make nice round numbers? Could I add things in various orders? I'm adding things that are adding themselves. Couldn't I reorganize that stuff? Isn't that how addition works? So if I'm adding a bunch of things that are adding, so I can add each thing separately and add them at the end, it's the same stupid answer. Yes? Yes?
So now we can factor out the stuff that we need to.
Now we can do like we did earlier. Yes? What does the summation symbol see as the variable? Yeah. So this is a constant, yes? So then what's the sum of a constant? What's the sum of 2 from I equals 1 to n? 2n. So what's the sum of that 1 to n? That times n. How many 12 over n's do you have in that summation? How many 12 over n's are in this summation right here? There are n of them, correct? From 1 to n. So I have n of these. N times this. Just like we did 1 to 38 of 2. I have 38 twos. So that's 38 times 2. I have n of these. So it's n times this. Let that be fantastic. If you add up a constant so many times, I just said the word times. That's where the idea of multiplication comes from. So this will be 12 over n times n. What comes out of this? 27 over n.
Oh, n squared.
Is it n squared? Yes, I left the square off. And then I equals 1 to n of I. And we know what that shit is, yes? Minus what comes out of here? Anything that's not I, because it's the I is the only thing that the sum sees as a variable. Okay. What I'm trying to do is I'm trying to strip it down to its I dependence. Because then do I have formulas that tell me how to do the sum of I and I squared? Do you have formulas that do that? If only. Yes.
What does the last one say? Infinity, but the other, like, you see where it says the sigma and then n is above it? How come for the last one it has an infinity?
Oh, I don't know. Thanks, man. Thank you. Yes. Taking out what? Oh, this. Okay. Let's do this. Okay, let's do this step by step. I have 37s. What do they add up to be? If I have 37s adding, what do they add up to be? 30 times 7, right? So if I add up 37s, do you see how that says the same thing? This is just 7 times 30. What if I add up n 7s? 7n, yes? Okay, so does it matter what this is? If I made it a 6, would it fundamentally change the answer? No, it would just be 6n, right? What if I made this w? So sum I equals 1 to n of w. What's that? wn. Okay, so how's everybody doing? So as long as the summation sees it as a constant, what's the only thing that the sum is allowing to change? I know this is a new idea for us today, but the only thing the sum is allowing to change is I. So if the inside is not dependent on I, it's a constant, according to the summation. It doesn't give a shit if something else outside of it sees it as a variable. Why would it care? The only thing it's letting change is I. Is that cool? I goes from 1 to n. 7's a constant, so I have n 7s, 7n. I have n w's, wn. Here, 12 over n is a constant, according to the sum. How many 12 over n's do I have? N of them. So I have n 12 over n's. Just like I have n 7s, so it's 7n. Go ahead. Oh, this one? Oh, so again, what's the only thing that summation sees as a variable? I. 27 can come out, so can n squared. Because they are constants in each term, so I can factor. If they're in each term of a sum, I can just factor them out. Good old GCF. Okay. So then this does exactly what you'd hope it would do. What can I replace this with? And don't forget your 27 over n. There you go, Jeff. Squared. And then minus, what can I replace this with? I never give myself enough room. It's amazing. There we go. Yes? What do you mean? Sorry.
Wasn't it in the beginning, minus first?
Minus first. No. So from the beginning it was, minus was right here. Right? 4 plus 3x minus x squared. Is that okay? Doesn't sound okay. Okay. So this came from 4, this came from the 3x, and this came from the x squared. Okay, let's stop for a minute. Because there are a lot of moving parts to this thing. So don't feel bad if there's like a lot coming at you. But again, it's the same old thing. I just care about one piece of this at a time. So this one, if it's not an I, it can come out. Because you don't want to take your eye out. Sounds terrible. So, and then you can replace this with what little Gauss dude figured out. You can replace this, and I forget who figured this out. If I had to make a bet, I'd say Gauss, because he did too much shit. But I don't think it was Gauss. I think it was Euler. I don't remember. Okay. But this is the feel for every one of these problems. You're going to have to figure out this. You're going to distribute the delta x. You can break each piece up. I would highly recommend you do that. You're going to take stuff out that's not I, and you replace the I stuff that's remaining with what you know it is. So what's the last thing you're going to always do is this limit. So what do you want to end up in here? The only letter that should be left when you're about to do the limit is N. So let me do this. I'll do part of it. The limit as n goes to infinity of 12 is 12. Good job, Jeff. Now somebody else do this part. Yes, the degrees are squared and squared. Coefficient of the top, coefficient of the bottom. So 27 over 2. And then this one, don't forget, don't look at 27 over 6. That's not it. What else is there? There's a 2 on the top. Yes, that would be the coefficient of the highest degree term would be 2 times 27 divided by 6. So I get 12 plus 13.5 minus something, 9. Go, Jeff, go. Which is 7.5. I think. Does that sound right? No, it's 16.5. Okay. What did I do? Who knows? Now, is that an estimate we just did? Is that an approximation that we just did? No. We just, by hand, figured out the exact area under this funky-ass curve. We relied on little Gauss dude, and I believe little Euler dude, when he was older than we did, to help us with the I stuff, but we did every other freaking part of the show. Yes? How do I check that? Turn it in, see what I say. But beyond that, how do I check it? If I'm on the test, I'm like, is this right? You just go. Just go ahead. Oh wait, go ahead and check that. Let's check it. Unless you don't want to. You can just sit there and stare at a wall. The wall was just learned this thing. Is this the right one? Probably not. Yes, it is. So you integrate from what to what? 0 to 3. 16.5. Right. Go Team Human. That's pretty good. So right now, all an integral means to us, when you see the elongated s with the dx, it just means finding the area between the x-axis and the curve, right? From blank to blank. I do want to say this. Somebody pointed out earlier, they asked about the dx, why it was there. This is probably the strangest symbol. This is one symbol. I think of this as, do you guys know what bookends are? Do you guys know what bookends are? If you have books on the shelf, you could put these little, they look like a little miniature forklift, but you shove them underneath and it keeps the book standing. You with me? So I think of this as a bookend symbol. So normally, like a square root is one symbol and it's got a defined inside. Yes? So if you put a 9 there, I know that means the square root of 9. This is one symbol. It means the integral of, and what is it integrating? What I put on the inside. When I integrate this, that seems to go away, but that's not true. We understand it's based on areas, but when we get to the point where we're going to apply the shortcuts, it's going to look like the x goes away. The last thing you want to do is forget it. It's very important. I cannot stress enough to you. That is really important, because later we're going to learn stuff where we have to do extra things to it, and if it's not there, you're not going to realize you have to do the extra stuff, and then you're going to, lose points. That's that. Yes.
So we got 16.5 with the answer. When we write it on the exam, are we gonna write it as just that with no unit,
Yeah.
we put like the limit as n approaches infinity equals 16.
Oh, well, all right. So I want to go back to here. Look, this is what kicked everything off, correct? So if this is the great thing about math. Write this down. Work it. All right, shut up. And then you get that. So what equals 16.5? The thing from the beginning. So you need to understand that. You need to remember that. Because sometimes it's really, if there's a lot of work between, you're like, what the hell did I just do? Has anyone ever had that moment in mathematics? If you haven't, that doesn't make sense to me. I've done it. I'm like, oh God, how's this work? Okay, I got 7. What does that mean? Shit, what? I forgot. Okay, so I've already got it there. So if you just do exactly this, you put this down, and you get this, and you circle it, I'm like, this is me. Tears of joy, happy. Yes? Okay. Not tear tattoos. I didn't kill anybody. I haven't been in prison. Just me. Is that okay? This is probably one of the trippier little things we've done partially because it's built on these summation of I stuff that you just have to take my word for it. And you're all like, I just met you a few weeks ago, man. I don't know if I can trust you. I like that. Don't trust me. Look that shit up. Okay. I could be lying to you. Some of the stuff I make up, you guys don't even know. Most of it I don't. Okay. So, let's do this. Let's do. Oh, here we go. No, that's not what I want. Where'd it go? No. Here it is. Okay. Was there another thing here? Yes. Oh! Did anybody do number 3? This is me doing the same thing we did earlier. So a lot of the time, I haven't used this yet, because I know I haven't said this yet. When you do the antiderivative of little f, we very often call it, or I call it, big ass f. So what's the derivative of f? It would be f prime. Is that cool? So this way is derivatives. If we go the other way, that's antiderivatives, and we normally call the antiderivative of little f, we call it big ass f. The book is not going to say big ass f, but it is going to draw a big ass f. So it's freaking big ass f. So what is the antiderivative? Take a moment and figure that out for that function that we've been working with. Figure out what the antiderivative is. Yes?
For the big ass f, when we go to the next level, for our derivative, we have prime, double prime. What is the next level?
Okay, I need you to understand. I am both so happy and frustrated that you asked that question, because there's no continuation, really.
Stays big.
Yeah. No, it doesn't just stay, we just give it different letters then. But we, like, for example, we call big ass f is the integral of little f, right? So then if I integrate big ass f, I can just call that g. There's no, like, continuing thing like derivatives have the prime and double prime and so forth. I mean, not really. All right. There sort of is, but it's in very specific contexts. We don't have to worry. We're not going to do a lot of like a bunch of antiderivatives in a row. We're not going to do that yet. What? So let me check. Did anybody figure out what big ass f is? Sorry, what is it? 4x. I like. 3x squared over 2. Good. Kick ass. So what is f of 3? Big ass f of 3. Yeah, it'll be 12. Let's see, 12 plus 27 halves minus 27 thirds. Does that look familiar at all? No? Okay. Not quite yet. And what do you get again? 16? I don't think so. Well, let's see. We get 12 plus 13.5 minus 9. 16.5, yeah. And what's big ass f of 0? I'm sorry, did you say 16.5? I heard 16. I'm sorry. That's my fault. Okay. And then f is 0. Big ass f of 0. 0. Yeah. So when I do get the same answer. It's a little underwhelming because of the 0, but we have still got to prove that connection. Do you all agree that antiderivatives by themselves, as long as the function is not too weird, is pretty straightforward? Yes, it's pretty easy. If you know your derivatives, you must know your antiderivatives. That's all there is to it. We don't have a way to do an antiderivative of like sine of x squared. I'm pretty sure we looked at that one directly because it's missing its chain rule piece. Okay. And to be really honest, I think I said this, sine of x squared is a function that you cannot integrate by hand. Yeah. Yes, okay, good. So let's do this. Actually, yeah, let's have an early day. You guys okay with that? Is anyone really upset about that? I have a feeling everybody's going to be okay with that. I think I've loaded a lot of stuff on you today, so that's fun. The last time we did 4-9. Today we did 5-1, 5-2. Let's have a quiz on Wednesday on 4-9, 5-1, 5-2. I made that sound like a question. Let me say it again. We're going to have a quiz on Wednesday on 4-9, 5-1, 5-2. Yay! Let me write it up here so it's official. Wednesday. Quiz. 4.9. Wait. 4.7. 4.9. Here, I'll just go up to 5.1, okay? 4.7, 4.9, 5.1. So there'll be optimization, antiderivatives, and the rectangles, right? The 6 rectangles, not the infinite rectangles. Did I get you got your stuff back? You did? Okay. It's probably right here. Hold on. Is it this? Shoot. What did we talk about? Oh yeah, we did. Here we go. We did this. I don't know if I have another sheet of this. Here we go. Perfect. It was this one here. 4.7. And there was one more thing. This one. Yeah. Sure. And then, fella, do we... Tomorrow morning, good. I got some other people coming. 8 o'clock. Hey. Your last
With like 8 miles.
Oh, I got to hear something. It's a T, right?
Yeah.
There you are.
Yeah,
So
so
this
I'm
I'm not going to give you because it's missing the test. Did we talk about makeup for this?
Yeah, is it possible tomorrow or?
Tomorrow will be great. Tomorrow at 8. I've got at least 2 other people coming. So we create that little group of you to do tomorrow morning. Yeah.
So I might have like a consultation today because my doctor asked like when my parents get out pretty late. So they said like a later. So I'm not sure. They said that it can be like super late today. My parents want to like sit down with them and talk about it.
Okay.
Or like transpire it to like Tuesday morning.
Oh, I see.
Yeah.
All right. If you can't make it tomorrow, we can try.
I will
to do
try
it.
that. I will, for
If you
sure.
can do, if not, we can do it a different morning.
Yeah.
I normally hear pretty early. I can be here at 8. It's not that big of a deal.
Okay.
Yeah.
I'll let you know beforehand.
Okay. Thank you. Oh. Yeah.
I want to give you a little update. I'm going forward with my college planning thing that I told you about earlier. It is taking an enormous amount of my time, which is why the homework for the last test was not done.